Hello, this is Deborah Barrett with the Cincinnati State Physics Department presenting Moving a Filing Cabinet, How Force Controls Motion, Part 2. This is a follow-up to the prior video, which also looked at moving a filing cabinet. Let's read the new problem. You need to move a 920 Newton file cabinet. The kinetic friction force between this file cabinet and the floor is 368 newtons. Suppose you push horizontally on the file cabinet with 506.5 newtons and it jerks into motion. Let's say the maximum static friction force is 506 newtons. What is the acceleration 1/10 of a second after the cabinet starts moving? We've already got a similar free body diagram here for the prior problem. We're going to have the cabinet's weight, that's given as 920 newtons. Since the cabinet is on a floor, which is presumably level, there will be a normal force that will be perpendicular to the floor, so that's drawn in vertical. We'll have an applied force, that's given in the problem as being 506.5 newtons. And the problem also tells us that the friction force between the cabinet and the floor is 368 newtons. So here's our free body diagram with the information shown, which was given explicitly. We can also determine the normal force. Since the file cabinet is not going to change its vertical velocity, then the vertical forces must be balanced. So the normal force must be 920 newtons. The problem asks you to find the acceleration on this file cabinet. All we have is force information, and they want the acceleration 1/10 of a second after the cabinet starts moving. So we don't even know the velocity at that point, but we can use the relationship that links motion and force. That would be Newton's second law, or Newton's first law if you have balanced forces. Right now we don't have balanced forces because the friction force is less than the applied force. That makes sense because right now we have kinetic friction because the file cabinet is now moving. And the kinetic friction force is not the same as the maximum static friction force. So the static friction force we had in the last problem no longer applies. Now we're looking at kinetic friction. To find the net force, we have to get the total of all the forces acting on the cabinet. We already know that the normal force and the gravitational force are going to cancel, so that leaves us with just the applied force of 506.5 newtons and the friction force of 368 newtons. Those two are acting in opposite directions, so we will need to subtract those in order to get the normal force. As in the last video, the mass of the file cabinet is 93.9 kilograms. This gives us an acceleration where, for the numerator, we have 138.5 newtons and a denominator of 93.9 kilograms. That works out to be 1.475, and the unit, as I showed on the previous video, simplifies to meters per second squared. So that's our acceleration for 1/10 of a second after the file cabinet starts moving. And actually, as long as the file cabinet is still moving, and as long as you're continuing to push with the same force of 506.5 newtons, you'll get the same acceleration, which means your file cabinet is going to accelerate radically more after it starts moving, if you continue pushing that way, than the acceleration it had when it first began. You remember that was on the order of 5/1000ths of a meter per second squared. This is an example of why you have to back it off some right after you get a heavy object started moving, because then the kinetic friction force takes over where the static friction force used to be, and the kinetic friction force is a lot less generally than the static friction force. So you wind up with a bigger acceleration, and to keep that from happening, you back off on your force. At this point, I'd like to throw in a little bonus and show you how you can get the coefficient of friction once you have found your friction force and your normal force. You remember from the lab and the textbook that the coefficient of friction is defined as the ratio between the friction force and the normal force. So, for example, in the case where the file cabinet is in motion, which is the example we've done just now, you have your friction force of 368 newtons. Your normal force is still 920 newtons. So that ratio will give you your coefficient of kinetic friction, kinetic because it's in motion. This works out to a 0.4 as the coefficient of friction. If I continue to assume that the 920 newtons is 3 significant digits, then I'm okay with you giving me either 3 significant digits or 4 significant digits in the answer, in which case you would have 0.4000. That's 4 significant figures, like I gave 4 significant figures in my acceleration answer. Notice the numerator and denominator of the mu calculation have the same unit of newtons, and so those two units are going to cancel and leaving you your coefficient of friction as a unitless answer. So I have my mu. In this case, it was a coefficient of kinetic friction because the force combination was for the cabinet already in motion. You can do a similar calculation for the cabinet when it had just started moving. Those forces were from the prior video where we had a friction force of 506 newtons divided by a normal force of 920 newtons, which would work out to 0.55 as our coefficient of friction. So there's a little bonus, both coefficients of friction for the file cabinet against the floor in this case. Thank you for studying these videos on using Newton's second laws to calculate accelerations.